Net ionic equations. So net ionic equations are used in double replacement reactions. And remember that with double replacement reactions, DR reactions, at least one of the products has to be a solid or water, and both of the reactants have to be aqueous ionic compounds. So the regular reaction that I would write would be saying silver nitrate, aqueous, plus lithium chloride, aqueous, yields silver chloride solid, plus lithium nitrate, aqueous. My ionic reaction basically presents everything in the state that they are in. So when I have aqueous silver nitrate, really what I have are silver ions floating around and nitrate ions floating around. And the same thing with lithium chloride. So in my reactants, all I have are a soup of ions that are just floating around, bumping into one another. What I'm saying is that as my reaction occurs, as my silver ions bump into a negative charge, sometimes if it bumps into nitrate, it will simply fall apart again. But if this silver ion happens to bump into chloride ions, they have a high force of attraction, and so they will come out of solution and form a solid. If my silver ion bumps into a lithium ion, nothing's going to happen because they're both positively charged. My lithium ion, if it bumps into this, it's going to be soluble and it will separate. And again, if it bumps into this, it will separate as well. So what's going to happen is that anytime my silver and chloride ions will bump around, I will tend to have a solid, but my lithium and nitrate ions will stay as aqueous ions, right? So these two are the same thing, but this is a way of being able to envision my aqueous ions as just freely floating around. So if a compound is written as aqueous, it actually means that they're freely floating ions. This also makes you understand why you have to have a solid, right? Because if I don't have a solid, if this was aqueous, then all I would have are silver ions and chloride ions floating around. My end result would look no different from my reactants. A reaction hasn't occurred if there hasn't been a change. If they started out as aqueous ions and they end up as aqueous ions, then nothing's changed. So that would be no reaction. And you'll remember that in some of your solutions, in your 8 solutions lab, you had things that were no reactions. And that was because even though you started out as aqueous ionic reactants, you didn't fulfill the second part of a double replacement reaction in that you didn't create a solid, and so all you ended up with were the same aqueous ions floating around in solution. So back to this one, really what's interesting is the silver ion and the chloride ion that have come into solution. So the real reaction is a silver ion and a chloride ion that used to be aqueous and now becomes silver chloride as a solid. So this is what we call the net ionic equation or net ionic reaction. It only shows the ions that react, that change into something else, right? Go from aqueous ions into a solid ionic compound. And the ones that stayed as they were, so lithium and nitrate that continued to be aqueous, just floating around in solution, those we call spectator ions. And we write the spectator ions, we say that they're aqueous, and we have to show the charge. So you have to show the charge, and you have to say that they're aqueous when you talk about your spectator ions. So the full equation is this. The net ionic equation would be a combination of saying the ions that actually do react, so they start out with aqueous ions, and they create a solid, and listing the spectator ions, remembering that the spectator ions have to have their charge, and AQ as a subscript. So my first example is sulfuric acid plus lithium hydroxide, both of them are aqueous, creating water and lithium sulfate aqueous. Excuse me. Water is the product of significance, right? So it's what prevents the reaction from just being no reaction because everything's just floating around in solution. So my net ionic equation is the hydrogen ion from the sulfuric acid and the hydroxide ion from lithium hydroxide combining to create water. That's my net ionic reaction. And lithium and sulfate are just spectator ions. So notice, I had to put a subscript here of 2 because lithium has a charge of +1 Sulfate has a charge of -2, so I have to create a product that exists. So it has to be Li2SO4. But when I talk about the spectator ions, I don't have to add coefficients. I do have to show the charges. So again, I'm showing the charge of lithium has a +1, sulfate -2, and I write the subscripts here. Lithium hydroxide and sodium chloride. Yield, sodium hydroxide aqueous and lithium chloride aqueous. It's no reaction. I have a soup of ions here and the same soup of ions here. Just because on paper you can have a double replacement reaction that works, doesn't mean that in the lab you actually see anything. So if you had this reaction in the lab, you would see no change, there'd be no precipitate forming, no gas, no nothing. You would see this as a no reaction because all the products are aqueous ions. They're just freely floating around. And then example C. Lead-2 nitrate, aqueous, plus potassium chloride, aqueous, yields lead-2 chloride solid, plus potassium nitrate, aqueous. This is the solid that forms, so the ions that are of significance that form that solid are the lead ions and the chloride ions. So my net ionic equation would be lead-2 ion, aqueous, plus 2 chloride ions, aqueous, yields lead-2 chloride. So even though my spectator ions don't have to have coefficients, my net ionic equation has to be balanced. So I have to balance it. So I don't have to balance this reaction, but I do have to balance my net ionic reaction. So again, lead-2 plus aqueous ions plus 2 chloride negative ions, aqueous, yield lead-2 chloride as a solid. I can go ahead and put a double-headed arrow because I know that there's a KEQ value for this. When I write my net ionic equation, I act as if there is no KEQ value, but we actually do have to acknowledge that. My spectator ions are my potassium +1 ion and my nitrate -1 ion, and they are both aqueous. And again, these don't have to be balanced. So what's important is that we use our net ionic equation oftentimes in KSP calculations. And so even though the net ionic equation is written as my ions, my aqueous ions forming a solid, when we do the KSP expression, remember that the KSP expression is always from the dissociation, so the solid becoming aqueous ions or the water forming aqueous ions. And that's really because you want your ions in the numerator. My solid or my liquid water will always be not part of my reaction, so rather than having it as 1 over my ion concentration, I just want to keep things simple and have my KSP expression just be my ion concentrations over 1.